Hi everyone, welcome back to Civil Engineering with Amir. This is Amir here with another video on the topic of shear force and bending moment. In the previous video, we analyzed a simply supported beam with a total length of L and a uniformly distributed load with a magnitude of W, and I showed you how you can write its shear force and bending moment as functions of X, and based on those functions we were able to draw the shear force and bending moment diagrams. So our load was constant with a magnitude of W, our shear force was linear, and our bending moment was a quadratic function. Now in this video, we are going to analyze the same simply supported beam with a length of L, but this time we have a triangular distributed load with the maximum magnitude of W and a minimum magnitude of 0, and we want to determine its Vx and Mx and draw the shear force and bending moment diagrams. Alright, let's solve this question together. We know the first step is drawing the free body diagram for this beam. So this is our beam, this is point A, this is point B. I'm just going to copy our load. We have AY here and AX, and we have BY here. Now in order to determine these support reactions, we have to write the equations of equilibrium for this free body diagram. So the second step would be, now we know in order to simplify this free body diagram, we can substitute our distributed load with a single resultant point load. The magnitude of our resultant point load will be the area under our distributed load. So we have a triangle, and the area under the triangle would be W multiplied by the length divided by 2. And we know that the resultant force will be applied at the centroid of our load. Now, since our triangular load's length is L, the resultant force will be applied at a distance L divided by 3 from the larger end of the load. So we had a resultant force with a magnitude of WL divided by 2 applied at a distance of L divided by 3 from the larger end of the load. Now in the X direction, we can write the only force we have in the X direction is AX. So AX would be equal to 0. In the Y direction, we have AY minus WL divided by 2 plus BY equal to 0. So AY plus BY would be equal to WL divided by 2. Now if we write sigma m around point A and choose this direction as the positive direction, we can say WL divided by 2 multiplied by L over 3 minus BY multiplied by L will be equal to 0, and this will give us a BY equal to WL over 6. And now if we put this BY in this equation, we're going to have AY plus WL over 6 equal to WL over 2, and this will give us an AY equal to WL divided by 3. And now we can substitute these support reactions with the values that we found here. So I'm just going to copy this free body diagram. WL over 3, WL over 6, and the total length of our beam was L. And now in the third step, we can cut the beam at a distance X from the left support and draw the free body diagram for any of the two segments. So if this is X from the left support, we can draw the free body diagram for either this segment or this segment and determine the shear force and bending moment for that segment. So step 3, so I'm just going to copy this diagram again and draw the free body diagram for both of these two segments, just to show you that you're going to get the same result. I'm going to start with the left segment. So I'll just clean this part. We don't need this. So this is our Vx downward. This is our Mx counterclockwise. And if you want to analyze the right segment, you'll have something like this. This is our Vx, which is upward. This is our Mx, which is clockwise. And the length of our segment will be L minus X. So this is L minus X. Now in the last step, in order to determine Vx and Mx, we can write the equations of equilibrium for any of these two segments. You can probably guess that this segment will be easier to solve because in this segment we have to deal with a trapezoidal distributed load. But anyway, I'm going to write equations of equilibrium for both of them. So step 4, for this segment, we can say our trapezoidal load is sum of a rectangular load and a triangular load. Now, in order to determine the magnitude of each of these two loads, we can draw our total load again. So this was W, this was 0, this length was L. We cut the beam at the distance X. So this is X. This will be L minus X. This is W here, and we can call this Wx, which we don't know its magnitude. Now, using the geometric relations, we can say Wx divided by W will be equal to L minus X divided by L. So Wx will be equal to L minus X divided by L multiplied by W, which will be this value here. And the magnitude of our triangular load will be W minus Wx, which is X over L multiplied by W. So if this is our trapezoidal load, we can say it's equal to a rectangular load and a triangular load. And now we can substitute each distributed load with the resultant force. So for the rectangular load, we have Wx multiplied by X as a magnitude of our load, which is applied at the centroid of the rectangular load, or X divided by 2. So we have Wx multiplied by X, or L minus X over L Wx. And this distance will be X divided by 2. And for the triangular one, the resultant force will be the area of our triangle. So for W minus Wx, we have X over L multiplied by W. The length is X, and the centroid will be X divided by 3 from the larger side. So somewhere here we have X over L multiplied by W multiplied by X divided by 2, or W over 2L X in the power of 2. And this distance is X over 3. Now we can simplify this free body diagram. This is our cut segment. This is point A. We have WL over 3 here. We have W over 2L X in the power of 2 at a distance X divided by 3. And we have L minus X over L Wx. This is our cut segment. This distance is X divided by 2. The total length is X. This is Vx. And this is Mx. Now in the y direction, we have WL over 3 minus W over 2L X in the power of 2 minus this one minus Vx is equal to 0. And this will give us a Vx equal to W over 2L x in the power of 2 minus Wx plus WL over 3. And if we write sigma m around this point O in this positive direction, we have WL over 3 multiplied by x minus W over 2L x in the power of 2 multiplied by this distance, which is 2x over 3 minus this force multiplied by this distance, which is x divided by 2 minus mx is equal to 0. And this will give us an mx equal to W over 6L x in the power of 3 minus W over 2 x in the power of 2 plus WL over 3 multiplied by x. So we determine Vx and Mx by writing the equations of equilibrium for the left cut segment. And now we can do the same process for the right segment and see if we get the same values for Vx and Mx. I'm just going to copy this. We know this value here is Wx, which we have determined here. And we can substitute this triangular load with its resultant force. So we have Wx multiplied by L minus x divided by 2, which is applied at L minus x divided by 3 from the larger end. So this is our simplified cut segment. This is point B. By was WL over 6. This is the resultant force, which is L minus x over LW multiplied by L minus x divided by 2, or L minus x in the power of 2 divided by 2L W. This distance is L minus x divided by 3. The total length is L minus x. We have Vx, and we have Mx, and this is your cut segment. Now, in the y direction, we have WL over 6 minus this value plus Vx is equal to 0, and this will give us a Vx equal to W over 2L x in the power of 2 minus Wx plus WL over 3. Now if we write sigma m around this point equal to 0 in this direction, we have this force multiplied by this distance, so L minus x in the power of 2 divided by 2L multiplied by W multiplied by L minus x divided by 3 minus WL over 6 multiplied by this distance plus mx is equal to 0, and this will give us an mx equal to W over 6L x in the power of 3 minus W over 2 x in the power of 2 plus WL over 3x. And you can see that these values that we found using this cut segment are the exact same equations that we found here by solving this cut segment. And now, using these equations, we can draw the shear force and bending moment diagrams for our beam. So, for the shear force, we have a quadratic equation. At x equal to 0 or point A, we had a support reaction equal to WL divided by 3. So, we'll go up. This is WL over 3. And then from 0 to L, this will be our equation, which is going to look something like this. And then at x equal to L or point B, we had a support reaction equal to WL divided by 6. So we'll go up to come back at shear force equal to 0. So this is WL divided by 6. And if we solve this equation, Vx equal to 0, we will get an x equal to 3 minus square root of 3 over 3 multiplied by L. So at this point, our shear force will be equal to 0. X is approximately equal to 0.423 L. Our mx is a cubic equation. At x equal to 0 and x equal to L, our moments are equal to 0. And we know since dmx is equal to Vx, at this point that our shear force is equal to 0, we will have an extreme point on our moment diagram. So if we put this x in this equation, you're gonna get an m equal to square root of 3 over 27 WL in the power of 2 or 0.0642. So at this point, this is our moment value, and our moment diagram will look something like this. So this is square root of 3 over 27 WL in the power of 2. This is 3 minus square root of 3 over 3L. So our distributed load was linear, our shear force is quadratic, our bending moment is a cubic equation. That's it. Thanks for watching this video. I hope you found it helpful. If you like this video, please press the like button. If you have any comments, suggestions, or feedback, please feel free to write for us in the comment section. And finally, please subscribe to the channel if you haven't already. Thanks again and see you in the next videos.